I'm going to present the work Amplified Nanoscale Detection of Labeled Molecules via Surface Electrons on Diamond. Hopefully, later on, it will make sense to all of us, this long title. Yes, we published this paper on arXiv a while ago, on May. And now we're looking forward to publish it on communication physics. And well, the main authors of this work are Paul and myself. Then we have Carlos, who helped us a lot. And indeed, this work is inspired on a previous work made by him. Then we have Ricardo Puebla from the University of Carlos III in Madrid, who helped us mainly with the data analysis. And then, of course, Jorge. So yes, let's start. So, okay, sorry. The study of structural disposition of molecules and their dynamics is essential in life sciences, and it is a long-standing challenge to detect them individually or to track their conformational movements, like it can be the folding process of a protein. So taking this into account, we developed a hybrid sensor, the one you can see here, made of an MB and a dangling bond that is capable of sensing a single molecule. So this hybrid sensor is made of an MB and a dangling bond. MBs are color defects that can be found in diamond. This gray square represents the diamond, and here we have the color defect, which is the MB. And the MBs are a good choice as quantum sensors because they work at room temperature. They can be easily manipulated with microwave radiation. On the other hand, they can be initialized and read out optically. And besides, they have atomic size, meaning we can bring them very close to the sample, which gives us, on the one hand, spatial resolution, and on the other hand, sensitivity. So with the MBs, we can sense samples that have a picoliter volume, while with standard NMR techniques, we need hundreds of microliters. So yes, these are the main benefits of the MBs. And on the other hand, the other component on our hybrid sensor is the dangling bond. These are unpaired electrons, unpaired valence electrons, that they are common on crystalline surfaces. So when you sharply cut a periodic crystal, there are some electrons that are unsatisfied, some dangling electrons, and these are what we call the dangling bonds. Also, they are common on diamond. So the thing is that these electrons that are on the surface, they are very reactive. They couple to other spins that are on the environment, so they are usually seen as noise source because they alter the magnetic signal that the MB perceives from the sample. But in our case, by manipulating them in a courteous way, we are capable of using the dangling bond as an amplifier. Since the dangling bonds are on the surface of the diamond, are closer to the sample, meaning that they have a stronger coupling, and this is the reason why we can use them as a bridging element between the sample and the MB. So,
any idea which is the density of dangling bonds?
Yes, that was a data that I was going to give later on, but it is 0.04 dangling bonds per nanometer squared. Later on, when I give other numbers, it will make more sense.
That depends on the material. material or on the way it's carpet or
Yes.
fabrication, or it can be clean or induce the application of the appearance of more? Or
Usually, the surfaces of diamond are treated to get rid of all these dangling bonds. But I believe that that number, that density that I gave, 0.04 dangling bonds per nanometer squared, is the natural dangling bond density.
and then, okay, as they are a kind of free electron radical, right?
Mhm.
So they don't react with something, creating another kind of chemical stuff, such that you lose this free electron, or is not?
They are immobilized. They are valence electrons from an atom, so they are localized. They don't move around. I don't know if that's what were you asking.
Hydrogen or whatever gets coupled or something like that. Is this possible or not?
I mean, they do couple with the environment. I don't know if that's what you're asking.
Not magnetically. What I mean is in a kind of chemical reaction, right? Because
Okay.
it's a kind of free, okay, not free electron. It's an electron which is some way localized there, right?
Mm-hmm.
And some chemical would, I mean, like the one we are putting there, and they create some bond, chemical bond, such that you lose the spin, right? Is that possible? Or it is stable in that way?
I guess that could happen, but what it is done, typically these molecules are not just flying around. They are in another liquid which immobilizes the environment. Okay, so yes, the thing is that this dangling bond can be used as a signal amplifier, and we.
You want to say that it's a valence electron, but you also say that it's an imperfection. So, for what is the valence electron? From the crystal structure about something that's like an imperfection, external imperfection?
No, I meant I called it imperfection because you have a periodic structure, and when you imagine a periodic structure, there are no edges, but it is a consequence of cutting the periodic structure. So on the edge of this periodic structure, there will be some electrons which are not coupled.
How do you review this number? It's something that if you put the crystal, you will always have like the base of the structure of the crystal, not like the one you put it. Like if you have a crystal, you put it, you have like free electrons that before was paired to the
Yes.
like, imagine like the crystal.
I
Yes.
yes.
How is it possible that you can reduce the number length?
Maybe I don't know, but I'm guessing that you could place some ions on top of it so they are not impaired anymore and they do not couple to the environment, for example. And that's something that came to my mind. I'm not really a specialist on that. All right. So the objective with this hybrid sensor is to sense the dipolar coupling between two labels. These labels are some tags that have to be attached to the molecule previously. These tags are just some small molecules with a free radical. They also have a dangling electron. And then these electrons, they do also interact dipolarly with the environment. This means that they establish a coupling with the MB, with the dangling bond, and in particular also between them. And this coupling, the dipolar coupling between these two labels, is what we call G. Okay, so the dipole-dipole coupling has a strong dependency on the relative distance. So by measuring G, we can infer the relative distance between these two labels and thus extract information about the structural about the structure of the macromolecule we are studying. So yes, the key thing here is to attach these labels on some interesting sites of the macromolecule we are studying. And then to be able to measure this G with the hybrid sensor. So once we have the system, we have a clear picture of the system with the two labels, with each an electron and the dangling bond and the MB, let's move to the Hamiltonian. So we assume we have an external magnetic field, which is of the order of 150 Gauss, and this magnetic field defines the z-axis. So on the Hamiltonian, we will have the zero field splitting of the MB and the rest of the interactions that arise from the presence of the external magnetic field. This is the Zeeman interactions. So we can see the Larmor frequencies of each element multiplying their corresponding spin operator. And then we have the dipole-dipole couplings. Here we have all the combinations between the elements, and this is the structure of the dipolar coupling, where these are the spin operators, and this is the relative vector between the respective elements. Then, last but not least, we have the control Hamiltonian. Here are the microwave radiations that must be applied over the system in order to control it. Interesting thing to have in mind is that our sequence is multitoned, meaning that we need single addressing for every element. This is, we need to control each element individually. So, yes?
Can you make the dipole-dipole interactions time-dependent?
Time-dependent.
For the dipole-dipole interaction.
If I can make them time-dependent. I mean, in principle, they are not, but if, for example, you're taking into account that these elements move, the dipole interaction will depend on the relative distance, so it will be time-dependent, for example. All right. So what I was saying is that we need single addressing to manipulate every element independently. So one may think, I mean, that means that we need different resonance energies for the different elements on the system. And one may think that all these elements, since they have an electronic nature, they have the same transition energy. But the truth is that the MB, for example, naturally differs due to the zero field splitting. And in the case of the labels, since they are free radicals on a molecule, the molecular environment naturally alters the resonance frequency of this electron. However, not to complicate ourselves and to simplify everything, we consider the Larmor frequency that corresponds to the electronic gyromagnetic ratio, and we added a gradient to distinguish the resonance frequencies on the labels and the dangling bond. So here we considered a gradient of 30 Gauss per nanometer, and these are the resonance frequencies that we achieve with this gradient. You can see that they differ in slightly 1 gigahertz or slightly smaller distance. But this difference is enough if we compare with the amplitude of the drivings, which is 10 megahertz. So yes, we have single addressing with this gradient. If we move to, if we move to a interaction picture with respect to what we call H0, we can simplify the dipole-dipole interaction to this other expression, where we can see that the dipole-dipole interaction is reduced to only set-set type of interactions. All right, so this is a thing to keep in mind. I will come back to here later on. And well, for the configuration that we considered, the value of G, this is the dipole-dipole interaction between the two labels, is of the order of megahertz. So once we have the Hamiltonian of the system, I will now present the sequence of pulses that we designed. All right, so each channel corresponds to a different element of the system, and it represents the pulse sequence to be applied over each element. The wider pulses correspond to pi pulses, while the thinner ones are pi half pulses. And then the color indicates the axis along which the rotation has to be applied. All right, so only the MV needs to be initialized, which is done optically, as I mentioned before, and we obtain a polarization along Z, and the rest of the elements start in the thermal state, which can be approximated with the maximally mixed state. And the thing is that this initial polarization of the MV can be transferred along all the elements with this castle-shaped structure. And well, the thing is that at the end of the day, the polarization of the MV, the final polarization of the MV, depends on the dipolar couplings and on these times that appear right here. So recalling the set-set structure on the dipolar coupling, one can realize that in order to this coupling to have an effect over the elements, at least one of the elements needs to be polarized along an axis perpendicular to Z. And this is what these pi half pulses do. So with these pi halves, they activate the effect of the dipolar coupling. And on the other hand, these pi pulses, what they do is they cancel the undesired dipole-dipole interactions, because only the dipole-dipole interaction of the elements over which these pi pulses have been applied will survive. So yes, at the end of the day, this is the polarization of the MV. This is the probability of the MV to stay in the ground state. And these terms right here are noise terms that decohere the elements of the system. So we can see that by tuning these angles, which depend on the couplings and the time that we live here, by tuning these times, we can get rid of all these noise terms, and we are left with a simple expression that depends on the G, the target parameter that we were looking for. Yes?
So with the noise terms, you mean the phase that element accumulates due to external stuff?
Yes.
And what is the condition to get this clean final probability? I mean, you make assumptions, I guess, like the noise is constant or things like that, right?
Yes.
It's interesting.
So you have considered the systematic error instead of the statistical error.
I'm sorry, what?
It is okay. The noise can be also independent, right?
Yes.
Yeah.
I mean, yes.
It's not necessarily the same.
Yep.
Completely random always.
Yes, this is just what we did to see that the decoherence on these places can be cancelled on a strategical way by selecting the correct phases for the. But later on, when we were simulating, we applied the effective decay of the decoherence that can be created with arbitrary noise on the environment. So, yes, the main characteristics of the protocol are that G is encoded in a very simple way. It is directly the frequency of the signal that we are measuring, and then that it is a robust protocol. We have the protection against dephasing by tuning these times. We can get rid of these phases. And then we have the dynamical decoupling due to the DIR structure. By this I mean the pi pulses. As I told you before, these pi pulses cancel the undesired dipolar interactions. So, okay, now what we did in order to prove that this sequence actually works and that to see that the hybrid sensor is actually beneficial comparing to the only MV sensor, we ran some simulations. So on the simulations, we consider all the elements of the system and we applied the protocol over the elements. And then we added also some detrimental effects, like it is the crosstalk, which is the phenomena that appears when you are targeting a given element with the microwave radiation, and other elements that are energetically close also see an effect of this radiation, an unwanted effect. And on the other hand, we also applied some decoherence with these times, the decoherence and the relaxation of the elements. And we applied all this via Limbland, a Limbland equation of this form. So we can separate the simulations we did into steps. First, we compared the signal that we achieved from the hybrid sensor with the signal that we achieved from the only MV sensor for a given configuration. And then, since the configuration of the elements plays a crucial role, we moved on to a more general configuration, which had a cylindrical symmetry. And moving the dangling bond, we carried out some other simulations. Well, later on, this second part will be clarified, hopefully. So, yes, I will show first, which is the scheme that we followed when considering the only MV sensor. It is practically very similar to this one, but we do not have the dangling bond. We only have the labels and the MV. And well, the signal that we obtained for the probability of the MV is also very similar. But the main difference is that in order to fulfill this condition, since this coupling between the MV and the label is around 8 times smaller than what it is between the dangling bond and the label, this time needs to be also 8 times longer. So you can see where does the benefit of the dangling bond arise, no? Because here, as we need longer times, the detrimental effects, like it is the decoherence of the elements, affect more. So yes, just as a data, if we take this t equal to 0, this sequence lasts around 15 microseconds, while this, when we take this t equal to 0, it lasts around 5 microseconds. So there is a difference on the time that we need to, that each sequence takes. Well, once this condition is met, the form of the probability of the MB is the same. So this is the outcome of the simulation we carried out. This is the probability of the MB to stay in the ground state with respect to the time t. This is time t. So we carried out several simulations with different time t's, and this is the collected signal. The blue line corresponds to the hybrid sensor, while the red line corresponds to the only MB sensor. So here we can already see a difference on the amplitude, but when we perform the Fourier transform, since we know that this signal directly depends on G, the Fourier transform of this signal gives us directly a peak on G. And here we can see that the amplitude that corresponds to the hybrid sensor is 5 times larger. This means a 5 times larger signal to noise ratio, which from the experimental point of view, it's well, very interesting. This can also be seen on the maximum likelihood estimations that we made. This is the real value of G, and these other ones are the estimations. And we can see that for the case of only MB, for this amount of repetitions, we cannot really see anything. We cannot really give an estimation of G, while we do using the hybrid sensor, at least for this configuration. And now, moving to a more general configuration, we aligned along this set. Yeah.
Okay, there's that one. 50,000 shot experimental, okay. So also, so you repeated each point 50,000 times, right?
Yes.
To accumulate enough photons or statistical stuff. Okay, but in any case, then the red one, the red line also takes 10 times longer, or not? Or am I missing something? Because you said that to achieve the conditions leading to this
yes, it takes longer.
Okay, 10 times more or less, right?
Yeah, we did for the same amount of shots.
Okay. So the same number of points?
Yes.
Where each point is
repeated
after repeated 50,000 times?
Yes.
But as each point takes 10 times longer, so essentially,
I mean, not 10 times longer. It takes like 3 times longer. It's at 5 and 15.
50,000?
I try to say it. 5 microseconds and 15 microseconds. So 3 times, not 5. But yes, there is a difference. And of course, this also depends on the dipolar couplings, so on the configuration of the system. So yes, we decided to move to a more general configuration, which is this one, where we aligned all the elements along the z-axis. And then we moved the dangling bond far away from this symmetry axis. So the thing is that this initial configuration where all the elements are lined up is the ideal for both schemes. It is the best one for the hybrid sensor, and also it is the best one for the only MB sensor, because the dipolar coupling depends on this angle theta, which is the angle that the elements make with the z-axis, And we can see that the dipolar coupling achieves the maximum value when this angle theta is 0. So the thing is that when we are moving the dangling bond farther and farther away from the symmetry axis, the hybrid sensor is going farther and farther away from the ideal configuration, while the only MV sensor stays in the ideal configuration. And the question here is, how far from the ideal configuration can we take the dangling bond and still benefit from using the dangling bond? So we are constantly comparing the ideal configuration of the only MV sensor with distinct configurations for the hybrid sensor. And these are the signals that we obtain. And here we can see that we can go up to a radius of 3 nanometers with the dangling bond. And, well, if you go farther than this, it's not beneficial to use the dangling bond, but it is up to this radius. And this radius, since we have a cylindrical symmetry, means that it is beneficial to use a dangling bond that is found on a 30 nanometer squared area.
This is for the 111 diagonal cut?
For the, yes, which is aligned.
And what would you expect that happens in a more normal diamond?
Well, in a more normal diamond, the dipolar coupling along set, so it would be weaker for both cases.
But why?
Because it's a different configuration. Now the surface is not perpendicular, now everything is tilted. So
Yeah, but because the same story applies to this direction, right?
Yes, it's a good question, but yeah, it would be detrimental for both kind of sensors.
If you have the reflection in the middle of between the NV and the
Level 1?
and the molecule, do we not have like a barrier effect, like you have like it will not affect because you have the two interactions between the imperfection and with the molecule. And if you put in the middle, like with the molecule, you have not like an effect that you put something in the middle.
Yes. That could happen, but we assume that we have no dangling bond when we are running simulations for the sensor that is only made of DMB. So we get rid of the dangling bond when we are running simulations that do not use the dangling bond. Okay, so as I said, this radius of 3 nanometers corresponds to an area of 30 nanometers. And with this density, superficial density of dangling bonds, indicates that we have one dangling bond every 25 nanometers squared. So this means that it is actually very likely to find a dangling bond that will be beneficial to use it as a signal amplifier. So, well, let me tell the conclusions of our work. So the protocol that we designed exploits the presence of this dangling bond, and also it is robust. So it diminishes the effects of the coherence because it only has a role on a very short intercommunication periods. Then, actually, employing the hybrid sensor gives a much larger amplitude. So then it is easier to detect the fluorescence oscillations of the MV, and then we can infer G easier. And also, we believe that it paves a way for new possibilities in quantum sensing of employing solid defects, because we are with this new idea of employing hybrid sensors that mix different defects. And for further study, we realized that in our sequence, or in our protocol, the most detrimental effect was induced by the decoherence of the dangling bond. So here we considered a decoherence time of 1 microsecond, but we ran simulations for different times, as you can see here. And we see that when the time is 1.5 microsecond, is 50 times better, so it has a 50 times greater amplitude than when comparing to 0.5. So the logical way of improving this protocol is to protect the dangling bond better from dephasing, which could be achieved, for example, with more dynamical decoupling, or with more pi pulses. And another alternative way is to create a protected state, so to drive the dangling bond to a protected state, for example, to a singlet. So we would need also another dangling bond, but yes, these are future works. And this was everything for today. So thank you very much, and thank you for your attention. And if you have any question. Okay.
No, maybe it was not clear why measuring G is interesting, because in some way was the target of your book, right?
Yes.
It's because I guess you can relate it with the.
Yes. So from G you can infer the relative distance between these two labels. So, for example, an idea would be to measure this distance between two labels that are tagged on a protein before and after the folding process, for example. So you can see how much closer they have gotten these interesting sites where you attached the labels, for example.
Yeah. So you could check what's going on, for example, with a certain molecule when you measure some oscillation, right, and you can detect the G. And from the G you can infer more or less the distance, or you will compare, right?
Yes.
And then you put this protein in contact with some kind of chemical or whatever that could induce or not, right? Some transformation.
For example. Okay.
And then you change it and you check again this oscillation, right? And if there is a change, you could see that this is important. You can assess that something happened.
Well, two questions. First, like at the beginning, you don't consider the longitudinal relaxation along the z-axis, and you obtain the formula for the P0, the 1 minus cos V. That's without the longitudinal relaxation.
Yes, that's right, because the relaxation times are much longer, so they do not play a crucial role. But then for the simulations, we did take them into account.
And the second is there is also like something called the transverse relaxation. I think when the spins have slightly different frequencies with respect to the frequency of the interaction picture, and then like they get dephased, and that gets like one as the other, like if you capacity in the polarization and in the signal. In the polarization in the signal. I think, do you remove that effect with the sequence?
I guess you're talking about the crosstalk. No, okay, no, you're not talking about the crosstalk.
No, I suppose you have like many spins in your sample, like when you when you make them rotate, they rotate frequencies and they
Okay.
Yes.
Eh?
T2 is that.
Yes. Okay. Yes. That is what we are capable of cancelling with the structure of our protocol. With the spin echoes, we are capable of going from the T2 star, which is that the time that corresponds to that effect you are telling us, to T2, which is a longer time.
and also the sequence apart from that, it gives you like a dependence on the signal, the dependence you want. Like that sequence, from that sequence you get that the signal at the end is that has that dependence on minus loss in
Yes.
over.
So what we do is we run, so this protocol should be run for different time t's and collect the luminescence you get from the MB. And this signal will oscillate with G. Anna, did you have any?
Yes, about the labels, you mentioned that those are free radicals molecule on a molecule, and how do you know where they are, or how much control you have with them? Maybe you mentioned that I didn't.
All right. So the question is how good you can control those.
I mean, how do you decide which labels you have on a molecule? You have a molecule with free radicals, you have information of those free radicals in advance.
So I know that some labels exist which are very good studied because they use it in biology experiments. So I think that you do have control to put them where you're interested. And then, well, with this protocol, the idea is to actually measure the distance between these two. So, yes, I guess. I don't know. I don't know about it.
I think if you have a catalog of small molecules, which are the radicals, and then one thing they do a lot in biology is that they create anchoring sites on purpose. So it's a small modification of the molecule, and then this radical can only join to those points, so you know it, and then you can measure that distance. They do it on purpose.
So you can manipulate the macromolecule you're studying in order to.
Anchoring sites.
Alright.
So this means that the proteins are created so that they tend to capture radicals, right? And and then you put in some solution radical or whatever some type, right? I mean, the most studied one. The good thing is that there is already at least one experiment in this direction, in which they were already able to measure the presence of a free radical attached to a certain big molecule through an M. And that is these horrible molecules who were suffering.
EPI.
Yeah.
Common experiments.
Yeah.
Okay. I ask a question. It's very interesting. You see, for each time you have a very elegant positive time. I ask you the question to you. Do you think you have a general, more elegant toolbox for designing such kind of process? Because I have the feeling that for each time you want to control the different things with different proposals, you have a very good elegant design, for instance, to make this theta 2 equals pi over 2, then you have the pi. I wonder for in the future, if you have a more general systems, do you have the toolbox to design this dynamic compositing to optimize all the things at the same time with not much effort?
Well, that's interesting. I know that there is a way to study how these phases, for example, affect. There is another way of analyzing things, different to the way in which we do, because it was more of a trial and error. We realized that there were different combinations of phases that also give the same result. But I would not say that we actually have a much controlled way to predict what's the outcome. But I know it exists a way. And yeah.
So at the moment, you were saying that for each setup or proposal, you need to care for all the detailed design.
Yes,
right?
for the moment it was more of a trial, I would say.
But the process is going to become more and more complicated.
Yes, like from the study of the evolution of rock, the matrix density of the whole system, and studying how the off-diagonal terms and how they evolve, there is another way to predict this thing different to the way in which we did. Because what we did was to take the Hamiltonian or mathematical or whatever, compute the analytical solution of the propagator that arises from this Hamiltonian.
Yes. So let me make one comment here, because here the interesting thing is that you don't have the necessity of scaling this, right? Because the important thing here was to measure this G, and with 2 is enough, right? Because the objective is to measure variation of these G's, right? Because of some change of the molecule, right? So in principle, there is no necessity of scaling the system, right? Meaning putting more layers, it's not enough, right? For the purpose.
Then your process is unique for this.
Is unique for analyzing yeah. I don't know, because I think we were doing once adding more channels. I think this cluster shape can be increased in some way.
Yes, or reduce it, like for the case when we don't have an Ampli one and still works.
Yeah, if there was another level, do you think it would be like you could scale that as easy as putting another line there, and this would let you detect all the G's at the same time? For instance, if there's another tag, you would get 3 different couplings that you would be interested in, right? Is that easy or not? So
I think
for you to do that,
you would need 3 measurements.
Yeah, I would separate them. And
That's what you
but not at the same time.
No, at the same time, it would be a combination probably.
But then you have more freedom.
more?
More freedom.
Yeah, with a triangulation, for example, you could get a more exact position.
Yes, how much time you want to spend?
Yes.
Yeah, but maybe it would be a combination of those 3, coupling constant and the frequency would go the 3 at the same time. I don't know. And you could do that once. I don't know.
So regarding scalability, the most interesting thing I guess is the issue of, instead of changing the targets, right, which is enough for measuring the G, without we get information to increase the number of dangling nodes that you mentioned, right? Because if you have 2 dangling nodes, that's much better, because you can create you can explain, right? Because
A protected state.
you can create a protected state, right? And that means that this P2 is very large, and then the signal is not. So that would be the end, I guess. It's not needed to go far.
I have a question about the maximum likelihood estimation. Can you maybe explain how you did this? Or because the signal looks really complicated, and usually you need
It is a fit of the signal with this function right here. and it's like a Bayesian analysis for different values of G, comparing with the one that fits with this point.
Yeah. Okay.
Alright. Okay. So, anybody? Nobody has any other question?